Lesson 9J, Efficiency. Efficiency is denoted with the lowercase e. It's a measure of the useful energy that you get from a system. Recall, not all systems are closed systems. Some systems have energy transformed into forms of energy that are not useful or intended, such as light, heat, or sound as a product of friction. The formula for efficiency is useful energy out divided by total energy in times 100%. Let's look at this example of a 100-kilogram person riding down a hill on his bicycle. He starts at the top of a 22-meter tall hill and begins with all of his mechanical energy as potential energy and none as kinetic energy. As he rides down the hill, his potential energy will transform into kinetic energy. If it is a closed system with 100% conservation of mechanical energy, then 100% of the potential energy will transform into kinetic energy. However, not all systems are closed. Some systems have some of the energy transformed into other types of energy that may escape from the system. Let's do the math to see if the example has 100% of the mechanical energy conserved, or is there some energy that escapes from the system as light, heat, or sound. Here are the known and given values. Initial height of the bike is 22 meters. The final height of the bike is 0 meters. The initial velocity of the bike is 0 kilometers per hour, or 0 meters per second. The final velocity of the bike is 50 kilometers per hour, or approximately 13.9 meters per second. We will calculate the energy that is lost, or escapes from the system, and then we will calculate how efficient the bike is in transforming the potential energy into kinetic energy. Let's calculate the energy lost. Remember that the sum of the initial energy must equal the sum of final energy based on the law of conservation of energy. That is, work in plus initial kinetic energy plus initial potential energy must equal work out plus final kinetic energy plus final potential energy. We will assume that the bike begins at the top of the hill, so there is no work required to move the bike to the top. So work in is 0. The bike starts from stationary, so the kinetic energy is also 0. The bike proceeds down the hill to the bottom, where the height is 0, so the final potential energy is also 0. That makes the sum of energy equation 0 plus initial potential energy equal to work out plus final kinetic energy plus 0. The initial potential energy equals work out plus final kinetic energy. If the bike is in a closed system and 100% of the energy is conserved, then the energy transformation would simply be initial potential energy equals final kinetic energy. Work out is the useless or unintended energy created as potential energy transforms into kinetic energy, usually a product of friction. Let's plug our numbers into the equation initial potential energy equals work out plus final kinetic energy. Potential energy is mgh, while kinetic energy has the formula half mv squared. Subbing in our values, we have 100 times 9.8 times 22 equals work out plus 1/2 100 times 13.9 squared. 21,560 joules equals work out plus 9,660.5 joules. Isolating work, we get 21,560 minus 9,660.5, and work out is calculated to be 11,899.5 joules. Energy that is lost or escapes the system due to friction is 11,899.5 joules. Let's calculate the efficiency of the bike. Efficiency is useful energy out divided by total energy in times 100%. In this case of the bicycle, useful energy out was the final kinetic energy that appeared as initial potential energy was transformed into other types of energy as it descended the hill. That makes the equation 9,660.5 joules divided by 21,560 joules times 100%. The efficiency of the bike in transforming mechanical potential energy into mechanical kinetic energy is 44.8%. This means that 55.2% of the original energy of the system, the initial potential energy, did not transform into kinetic energy, but rather was lost due to friction as light, heat, or sound.